Hey there, and welcome back. So this week we're going to take care of Lab 11, Chapter 13. And, I don't have anything to talk about as far as SolidWorks goes, but I do want to talk more about sheet metal. This is something you're going to cover more in 1109, but I want to, go ahead and get some concepts established. In an earlier lab, in 1105, I talked about it, but that's really about all that we've had exposure-wise to this. So, I guess first we should talk about the assignments, but then that's all I'm going to finish with is sheet metal, and then we'll adjourn. So do your lecture discussion board. Go ahead and read your chapter, work through your exercise. And if you notice, there's only 3 total this week. That's because they take a little more time. So one thing they do talk about here is K-factor. This is mostly going to be an amount that you set as your default in SolidWorks, and you're never going to mess with it again. Basically, it describes it as the neutral axis in a bin, which is what everybody calls it. And it's really something that when you're working at a company, they'll tell you what the K-factor is, and you'll set it and forget that it ever exists. But yeah, it's basically what they use to calculate the bins on a part. That's more or less the simple explanation. And as you can see, there's formulas for it and all of that. But you're going to use this K-factor in all kinds of formulas for other things. So when you're doing parts like this, where you make a part flat and then you make bins out of it, these numbers have to add up. If someone's going to fabricate something like this, everything's got to add up right for them to make it properly. So you use these base numbers, and then you model to certain design criteria to make it work. And that's more or less what they cover here. It's more technical in SolidWorks. In Inventor, you can be a little more loosey-goosey about it, but you really got to be methodical in SolidWorks. It's pretty quick to throw up a problem, but basically what you're doing is making the base area and then throwing in some flanges, which are basically, as you can see, like a bent from the original part extension outward in whatever direction. And then there's tabs added. And it's a whole process, really, but this is one of the things that you're probably going to use a lot of. And honestly, I think sheet metal is just as fun as can be. At first, I hated it, but it's one of the only areas in companies where there is no creativity that you still have to do something creative, and really express yourself. So I'm a big sucker for doing something custom. But anywho, so once you do that, you're going to have these 2 bad boys, the coolant fan cover. It's kind of a similar concept. You've got flanges and tabs with your base shape. Now, if you notice, you're back to making drawings. So you need a model and a drawing for these. And you should have a set of notes. Like on this one, there should be a set of notes above title block. And in this one, it's super straightforward. It's just a transition, but you still need a drawing for it. And, obviously it goes without saying, both of these, you need to have the regular model and its views and a flat pattern view as well. So make sure you've got those. So having said that, a long time ago, I really had to teach myself most of this about sheet metal, but this was my go-to website, sheetmetal.me. Take note. I don't know who these guys are, but they're legends, clearly. They talk about K-factor pretty well right here. If you want to read more about it, check it out. But the things that I wanted to talk about are somewhere here on the website. Let's see. So they talk about bend angles. And, when you're looking at these sheet metal pieces, that's all you're doing really is saying, like, something like this, that's a 90-degree angle. These angles can vary, but what you're doing is you're using those angles in your formulas. So it's good to actually note that although you have parts with depth, at the end of the day, you're still treating it like a regular angle. And then you've got things like bend allowance, which is directly correlated when you're looking at the flat pattern, how you get the difference in values, 4.92 versus, like 3 plus whatever, 0.5. So 3.5 obviously doesn't equal 4.92. That's where the elongation of a part being unfolded comes in. So like you can really see it explained here, but basically this area stretches and compresses when you unfold it, because that's what's happening. In order for this part to keep that same material thickness, it has to somewhat change in shape as it's grown or shrunk, when it's being rolled. So there's formulas for that, and they're pretty standard. Once you get more familiar with the stuff, you can actually set them into like formulas, it's called in SolidWorks, or parameters, it's called in Inventor, and you can basically for these bend allowances using formulas like this, which is pi over 180 times bend angle. I think that's what B equals here. But yeah, bend angle times the inside radius, which is the bend radius, plus K factor times material thickness. And the bend radius is always going to be the inside radius of a fold. You know, it's a common formula, and you know, it's pretty boring sounding stuff, but it's pretty much a need to know. The same concept pretty much applies to deduction. You know, like you saw in the other picture earlier, this is the same one. It's basically if you were to take overall values like the 2, 3, you know, you get your 2, 3 here. What would be the overlap value? You know, like that's kind of what they're doing there. And the difference here is you've got flange lengths, and this is the bend length, basically the bend allowance. It's a difference between the two in that case. Other than that, you know, a similar concept is, and this one's actually really easy to calculate, but the inside setback and outside setback are basically how far from that round to the theoretical vertex, as if there wasn't a bend. You know, like that's basically what's going on there. And they had those, and they kind of showed what it would look like on an angle. You know, it's a little more pointy, but same concept. And you know, basically, here's your formula. But outside setback isn't too bad. But here's an application for why you need to know this. If you are basically setting things up in a way to where they mate with each other, you have to know where they're going to end and the difference, so you can basically trim it right there. You know, like that's the idea behind it. There's an application for it, and you're not going to really dive into any of that here, but you know, knowing, I think the biggest part that really helps you with modeling this dude is knowing that when you flip where it's bending from, you are directly affecting this. You know, when you can visualize and say like, oh, this vertex matters, you can say, okay, well, you know, clearly the goal here for these flanges is they should start at the end of the flange. Instead of bending and intersecting into this metal, they're starting at the end. You know, like in 2010, the tabs and everything were all flush on this edge, and it was a lot more work, honestly, but you know, just knowing that those are there, it's going to be helpful. And then we talked about K factor, but yeah, so the big takeaway to me personally is go check out sheetmetal.me, study up on some sheet metal, and prepare to implement more of that information into 1109 when you take it, which is all about sheet metal and auxiliary views. But all right, so you know, finish up Lab 11 stuff, and if anybody has any problems, just let me know.